So Colin has been here for what, 11 years, Colin?
12.
12 years. So undergrad, master, PhD, and even a break in between, he was working at UCI. I mean, it's like his home. And I would say he also has benefited the place and contributed to the place a lot. So just to mention only one thing, UCI DBF. So Colin is one of the best students ever who is doing DBF, Design Build Fly. And when he was in charge as a student and as a maybe co-advisor, coach for the team, we got in the first 3 places international and the international competition of AIAA DBF for 5 consecutive years. And just to prove himself, he stepped down for the 6th year. We did not even make it to the finalists. So so this is like if and only if condition kind of proof for mathematicians. But anyway, so and here is his PhDs, also design, build, and fly, and some analysis, because it has to be a PhD for an unconventional flying vehicle. Without taking too much time, Colin, the floor is yours.
All right. Well, I want to thank everybody for coming to my presentation about multi-rotor vehicles with cyclic and collective pitch control. This presentation is an overview of the design, build, and testing of this configuration, some of the challenges encountered, and then some analysis to more deeply understand those challenges. And of course, during the presentation, if there's any questions, I'm happy to answer them. All right, let's begin. So the overarching motivation for this project is the surge in interest in urban air mobility and electric vertical takeoff and landing aircraft. As you can see, there's a variety of different configurations, and these aircraft have utility in passenger transport, payload delivery, and other commercial applications. Developing a deeper understanding and intuition about these configurations will be important for integrating them into the aerodrome and building public acceptance, which is critical to the success of urban air mobility. The specific background and motivation for this particular project is taking the more ubiquitous quadcopter and asking the question, if we replace the fixed pitch rotors that vary RPM for control with more conventional helicopter rotors that vary blade pitch for control, what sort of benefits may we see, and what sort of challenges may we encounter? Some of the proposed benefits are the ability to accommodate unique payloads, increased efficiency and agility, more robust control and unique control allocation strategies, and an expanded flight envelope with the possibility of performing auto rotations, which is something other multi-rotor configurations cannot do. There are a number of different multi-rotor configurations to try to address some of these proposed benefits. Besides the familiar fixed pitch multi-rotors, there are variable pitch multi-rotors, and these are similar to this configuration, except they only use collective pitch for control. And for those of you that are unfamiliar with helicopter rotor mechanics, collective pitch is when the blades all change together, and cyclic pitch are when the blades change at different points during the rotation. And this allows the generation of forces and moments, and is generally how helicopters adjust and control their attitude. There are non-planar rotor configurations that arrange the rotors at different positions and angles on the body to more directly control the given axes. There are over-actuated configurations that still use fixed pitch rotors, but allow the rotors to tilt or swivel to increase their maneuverability. Some adaptability, and this is specifically for failures of one or more of the rotors, but normally this would make the vehicle uncontrollable. However, the control system adapts and allows the vehicle to go into somewhat of an uncontrolled rotation about the vertical axis, and the remaining rotors are then modulated, almost like an artificial swash plate, to control the vehicle and make a safe landing. And then there's this collective and cyclic control configuration, and I believe it can blend some of the benefits of these other configurations, but that's not without some significant challenges. One notable previous work is the Piasecki multiple helicopter lift system that evolved into the Piasecki PA97 helostat. There was a fair amount of research performed on this configuration, and a prototype was developed. Let's start that video.
We have the liftoff. Unanticipated vibration rattled the frame. Seconds later, the right rear helicopter breaks off. Fall to the ground.
So as you can see, during test flying of the vehicle, it encountered some severe vibrations and was subsequently destroyed. And this was certainly taken into consideration during the development of this project. For the vehicle design, it was important to use as many commercial off-the-shelf components as possible to reduce prototyping cost and time. Commercial off-the-shelf model helicopters were used for the rotors, and 3-bladed rotors were chosen for vibration considerations. The airframe was built up from carbon composite tubes and 3D printed structural joints. The H-frame configuration was chosen to simplify installation of the rotors and the firmware modifications necessary for control allocation. There are 16 actuators on the vehicle, 3 servo actuators and 1 motor controller per rotor, making it an overactuated configuration. The table on the right shows the initial control allocation strategy chosen, and you can see it uses mostly cyclic pitch for control. For pitch attitude control, coordinated longitudinal cyclic is used. For roll control, coordinated lateral cyclic is used. For yaw control, it uses differential cyclic pitch. And because cyclic pitch cannot effectively control altitude, coordinated collective pitch is used for altitude control. Some vibration considerations taken into account during the design of the vehicle are that helicopter vibrations are generally dominated by the main rotor RPM and n times the RPM, where n is the number of blades. This table was developed during flight testing, and it shows that there's a narrow band of RPMs where the vehicle vibrations were deemed acceptable. So this means they were unobtrusive to being able to tune the flight controller and pilot the vehicle. However, deviating below or above this band, the vehicle would encounter some severe vibrations. And I thought that this quote is particularly interesting. It's from one of Ray Prouty's articles, and it says, "The late Bob Wagner used to give guidance to the designers by telling them to design everything in resonance as a way of ensuring that everything would be out of resonance when it was built." And I like this quote because I think it shows some of the challenge and frustration in working with rotorcraft vibrations.
Colin?
Yes.
Can you go back to the collective cyclic? No, yeah, that one.
Yes.
So regular quadcopters can control their yaw somehow, even though they don't. Each propeller is fixed.
Yes.
Right. So what you're doing here is using the cyclic with 4 rotors. So is this the only way to control the yaw in all 3 axes? Or is there an arbitrary linear superposition of coefficients for longitudinal, lateral, differential, cyclic, and collective that you could, in principle, think of? This is just the most straightforward one.
All right, so that's an interesting question. And actually, when we get into the control allocation strategy portion, we'll discuss that a little bit more. But right now, the initial control allocation strategy chosen uses just cyclic pitch for yaw control. However, we could use things like collective pitch or even vary the RPM. So we have a number of different methods to be able to do this. And even with cyclic pitch right now, it's just using longitudinal cyclic that's differential, but we could also use differential lateral cyclic. And depending on the geometry of the vehicle, even with cyclic pitch, if the geometry is not completely symmetric, like if it's not a square, then this would actually change a little bit in how the vehicle would respond to a yaw input. I think that answers your question, does it?
Yeah, thanks.
Okay. All right, the PICSOC 2.1 was used for flight control and data capture. Cyclic and collective pitch mixing is performed inside the flight controller, and the throttle signal is fed through directly from the receiver to the motor controllers. This is due to lack of output channels on the flight controller. However, for an expanded flight envelope and to explore some of these other control allocation strategies, it would be important to be able to control the RPM of each individual rotor from the flight controller itself. This is frame design 1, and this was the initial flight frame. And really what I want to draw your attention to here are the strut braces that go from the fuselage about halfway out on the rotor arms. These strut braces were added prior to the first flight. The initial frame did not have these, but after installing the rotors, it was noticed that the frame vibrated at quite a low frequency, and there was concerns that this would be excited during flight. So preemptively, these strut braces were added to stiffen the frame and increase at least this particular natural frequency. There were approximately 10 test flights performed for the vehicle, both in forward flight and hovering, to tune the flight controller gains, analyze power consumption, explore the operational envelope of the vehicle, and then assess cyclic pitch as a method of control for a multi-rotor vehicle. And from the pilot's perspective during test flying, it was noticed that the handling qualities were similar to that of a large fixed pitch multi-rotor. And this was encouraging because it would suggest that being able to incorporate this method of control into a current mission or being able to transition from piloting a fixed pitch multi-rotor to this type of control strategy could be done with relative ease. However, the frame had some significant vibration issues. The video on the left shows one instance where shortly after takeoff, it was noticed that the right rear rotor started vibrating. The rotors were powered down and a controlled landing was made. There's only minimal damage as one of the strut braces became debonded from the rotor arm. After repair and some slight modifications, flight testing began again. However, during another instance, while the vehicle was in hover, it was noticed these vibrations again. And this time, there was inadequate amount of time to be able to power down the rotors and make corrective action. And the vehicle began vibrating and this increased, and two of the rotor arms broke in flight and the vehicle crashed. And the picture on the right shows one of those rotor arms. And this was actually a bit surprising because these are pretty substantial carbon fiber tubes. So to see them break almost like toothpicks was a surprise. Now looking at the acceleration power spectral density plot from that flight, this is data captured on board the aircraft, we see some distinctive features. First, we see the bands of energy that come from the rotors. We see it very brightly, we see the main rotor RPM, and we see n times the RPM, which was mentioned before as dominant sources of energy. We also see this big bright line, and this is the time of the event. This is where the destruction happened. And what you'll notice is just prior to this happening, the RPM was increased because during this test flight, we were trying to explore the operational envelope of the vehicle. So you can see before we were operating in this acceptable range of RPMs, and then we wandered into this range of RPMs that create high vibrations in the vehicle, and the damage occurred. So at this point, I took a step back and thought, it'll be important to perform just a simple FEA analysis to try to get a better understanding of the structural dynamics of the vehicle. And what was encouraging is mode shape 3 represented clearly what we saw just prior to failure, and the predicted frequency was actually quite close to the main rotor RPM at the time of the failure. And this was encouraging because it would suggest that even this low fidelity simulation that's omitting some of the other dynamics in the vehicle could be used to help us propose redesigns and assess some of the behavior of these new structural changes. So this prompted frame design too. So you can see here the strut braces were extended. They go now from the fuselage all the way out to the rotors to effectively eliminate in-plane bending of the arms. The repaired arms use a larger diameter carbon tube, and these structural joints were all made more substantial. Another slight change that actually might have modified some of the vibrations that make it to the flight controller is in frame design 2, this structural interface that's between the rotor frame and the airframe was slightly undersized to allow a thin layer of hot glue to be placed between the rotor frame and the airframe for some vibration absorption. In the initial design, this structural joint was sized so it fit pretty snug into the rotor frame. But what was noticed in the second design, where the hot glue was included, the rotor had a much more secure attachment to the airframe. And it's possible that this may have facilitated some more vibrations making their way to the flight controller. And the reason I say that is, with the first design, even though it was a pretty snug fit, the rotor could slightly move on this joint, and this may have created a zone for absorbing and dissipating some of this energy. So this is not immediately clear, but things like this we need to keep in mind as we're proposing changes. So we begin flight testing again, and after there's some different flight tests, some modifications, we encounter the second instance of major structural damage. We are hovering the vehicle again, and this time we noticed the fuselage bending in plane. And just like last time, there was inadequate time to be able to make corrective action, and this time the fuselage broke in half. But we were operating the vehicle in this range of acceptable RPMs. So once again, looking at the FEA analysis, mode shape 2 represented quite clearly what we saw just prior to failure. However, the predicted frequency did not match the RPM that we were operating at. So it wasn't immediately clear what may have initiated this damage. However, what was clear is that the vehicle seemed quite susceptible to in-plane motion and damage as a result. So after repairing the fuselage using a carbon tube joiner and some carbon fabric wrap, these lateral strut braces were added to effectively eliminate all in-plane motion of the airframe. Consulting the FEA model once again, we see that there's one remaining mode shape and frequency kind of within this range of frequencies that have caused damage up to this point. However, when we look at frame design 1 and compare it with frame design 3, looking at these acceleration power spectral density plots, we see some noticeable differences. For frame design 1, and this is arguably the best flight that the vehicle had, we see that the bands of energy coming from the rotors are quite narrow. They're pretty consistent, and there's not a lot of energy between the bands. But looking at frame design 3, we see that the bands are wider and they're more noisy, and I would argue that there's a little bit more energy content between the bands. Additionally, this is a little bit more subtle, but if you notice for frame design 3, I'm only flying the vehicle in kind of short hops. Well, this is partly because I'm a little bit nervous since, up to this point, we've had a lot of damage in flying the vehicle. But this is also due to the fact that the vehicle is more difficult to control. The flight controller is more difficult to tune because of these vibrations, and this makes the vehicle hard to control bad handling qualities. So what's interesting about this are these changes that were made to the airframe to try to make the vehicle more robust and less susceptible to vibrations seems to have overall reduced the performance of the vehicle. And it was at this point that it seemed critical to dig into this interaction between the rotors and the airframe a little bit better and try to understand how the aerodynamics of the rotors might be affecting the structural response in the vehicle. And then this can lead to some interesting thoughts about how you might suppress or attenuate some of these vibrations, either using passive methods by including damping elements into the frame, or using some sort of active vibration attenuation method. It's an overweighted configuration. We may be able to allocate a little bit of power to be able to modify the response. And then we should look at a stability and control allocation analysis. Again, because this is an over-actuated configuration, we have a number of different control allocation strategies, and we want to explore those. We also want to see how these choices may influence the response, the structural response in the airframe. So let's first look at—
Colin?
Yes.
I have a question about that plot there, which is a really beautiful way to analyze your structure. ArduPilot has all these logging parameters built in, right?
Mm-hmm.
So you're using the logs to the SD card of the, or do you have a diff of the onboard accelerometer from the flight controller, right?
So just like you said in the first part, I am using basically a little SD card in the Pixhawk to record this data and extract it. So
I'm just pushing you a little on this because it's really significant and really interesting, because the chief software architect of ArduPilot, Andrew Tridgedale, I didn't watch it a lot, but he had a 1-hour video on log analysis from ArduPilot just last month. So they seem to be continuously developing tools within ArduPilot ecosystem to do vibrational analysis of lots of things. Yours is a very unique and interesting use case, but they do it for more traditional things. I'm wondering if have you kept up to date with all of their tools, or is what they have just basically a dump of the accelerometer and that's good enough and you do the rest on your own?
So to answer your question, no, I haven't kept up with this because actually, for one thing, all the flight testing took place a year and a half ago, almost 2 years ago. But what's really the issue here is I think moving forward, it might be good to get away from recording this data on the flight controller itself and instrumenting the frame with accelerometers to get a better idea of how individual parts of the frame are actually responding. So, if I had more time to work on this, I think part of the future work would be including a microcontroller and outfitting the entire frame with accelerometers in different locations to get a better map of what's going on, in addition to possibly capturing data using the flight controller. But part of the reason I say that is depending on how you mount the flight controller and where it's located will affect how it's seeing the vibrations in the frame. So it's not the complete story. And that's why I think it's important to have a better picture of what's going on.
Okay, thanks.
Okay. So let's first look at the coupled aeroelastic flight dynamics analysis. So looking at frame design 1, frame design 2, and frame design 3, we identify some mode shapes and their predicted frequencies that, like I said, have fallen in this band of frequencies that have been problematic up to this point. So the initial idea was take the rotors and calculate the stability and control derivatives of each individual rotor, and then integrate these values into the FEA model, specifically the damping parameters, to try to see how this affects the structural response. But this was proving exceedingly difficult to be able to integrate these into the FEA model. So instead, a reduced order model was developed. The schematic on the right shows the methodology behind this reduced order model. So in this case, Ka and Ca represent aerodynamic spring and damping constants that would come from the rotors. And Ks and Cs represent the structural spring and damping constants that come from the structural arrangement. Pictures on the left show how the frame was decoupled. So essentially at this point, the frame was decoupled into sections that could be treated similar to cantilever beams. And this is how the mass spring damper model was built up. A significant amount of time was spent developing the code to predict these stability and control derivatives, and then validate this code using published helicopter data. And one of the challenges here is that often the published helicopter data was omitting critical geometric parameters of the helicopters that were necessary to calculate these stability and control derivatives. So you had to comb through data and then piece it together and make reasonable estimates. In addition, the rotors used on the test vehicle, these parameters also had to be measured, and sometimes this included developing a small test to do so. For the mathematical structural model, as I mentioned, the frame was decoupled so you could treat it like cantilever beams. So taking some structural equations for bending and torsion of cantilever beams, these are rearranged to essentially extract the equivalent spring constants for those sections. For in-plane bending of the rotor arms, it was assumed that inside of the strut brace, the frame was essentially rigid. So all of the compliance was assumed to happen outboard of the strut brace. For out-of-plane bending of the arms were assumed to bend near the center line of the fuselage, and the structural elements were added as springs in series and parallel where appropriate. For torsion of the arms, it was also assumed that inside of the strut braces, the frame was essentially rigid. For bending and torsion of the fuselage was cut in half, and the cantilever beam was fixed at the center location. Now, this is not a perfect assumption, as the frame bends a little bit more like a free beam with masses at the ends, but at least for this reduced order model, depending on the mass distribution, this can be an okay assumption, at least to get us started. But there are some more in-depth methods to have a little bit better estimate, depending on how your mass distribution is on the frame. So after calculating the stability derivatives of the rotors and then the structural constants from the arrangement, I combine them together in what here I'm calling an augmented A matrix, but this should not be confused with an augmented A matrix from a flight dynamics standpoint. This does not include feedback control. What this is just a compact way to be able to combine these, because perhaps you're calculating the stability derivatives from a flight dynamics analysis, and then you're calculating the structural constants from a structural analysis. And this is a nice way to put them together so that you can quickly compute the eigenvalues and the response in the airframe. So to visualize this better, I use vibration transmissibility. And this is a really nice way to see the immediate effect that damping has on the response in the airframe. So looking at the arms, we see that the dashed line represents the undamped response, and then the emboldened colorful lines represent the damped response for these particular modes. So what you notice is that for the arms bending out of plane and the arms in torsion, there's a significant reduction in the transmissibility when damping is considered. However, looking at the arms bending in plane, we don't see the same reduction. This has pretty high transmissibility compared with the other modes. Looking at the fuselage, we see something very similar. The fuselage vibrating in plane has a much higher peak transmissibility than the fuselage in torsion or the fuselage bending out of plane. And what's really interesting is when you put these all together, considering the damped response, it reads a little bit like a time history of how the vehicle sustained damage during testing. The highest peak transmissibility, considering all the modes, is the arms bending in plane. And that was the first instance of structural damage. The next highest peak transmissibility is the fuselage bending in plane. And that's the second instance of damage. So looking at this, we can kind of get an idea of what modes are still susceptible, including the damping, and where we might look to next for damage to occur. And what's really important is when you superimpose onto this some known sources of energy and their predicted frequencies, we get a better idea of what can excite these modes. So for the arms bending in plane, when we line up the RPM just prior to that failure, we see it matches pretty well with the predicted frequency. So it's pretty clear that this is what initiated that mode and that damage. But as I mentioned before, for the fuselage bending in plane, we are operating in that range of acceptable vibrations, and the predicted frequency didn't line up that well with the main rotor RPM. So it wasn't clear what happened at the time, but once you consider the maximum speed of the servo actuators, it actually lines up pretty well with the prediction from the reduced order model and the Fea model. So the way servo actuator specifications are quoted is a time to move 60 degrees depending on the voltage. We were operating these servos at 6 volts, and this is approximately 19 hertz. Now this is a no load speed, and the servos are certainly under load. However, we're also not moving 60 degrees. So considering all of this, it's still very possible that this predicted mode falls within the actuator bandwidth. And I brought back this chart showing the control allocation strategy because specifically for the current strategy chosen, yaw control is from differential cyclic pitch. And this allows the generation of in-plane forces at the rotors. And it just so happens that during this test flight where this happened, I was tuning the yaw gains. So it's very possible that a bad yaw gain created a little bit of coupling and feedback between the flight controller and the structure, and this excited that particular mode. So now we go back and we look at the frames and identify predicted frequencies that fall within this actuator bandwidth. And we see for frame design 3, there's still one remaining within this band. So looking again at frame design 2, we can see clearly how in-plane forces of the rotors could excite this motion. Well, looking at frame design 3 and that predicted frequency, it's not immediately clear that this could happen. So we need to bring in a different control allocation strategy, specifically using collective pitch for control. So when you're using collective pitch for control and you put in a yaw input, 2 of the rotors across the diagonal from each other modulate their thrust in the same direction, and the other 2 rotors modulate their thrust in the opposite direction. So this creates a torsional action about the longitudinal axis of the frame. And we can see here that a bad yaw gain could once again create some coupling and may excite this particular mode. And this is also susceptible to the direction that the rotors spin in. So I've encountered this before. It was with a fixed pitch rotor, but I was flying this large fixed pitch rotor, multi-rotor for a group, an undergraduate group, and the frame was too torsionally flexible along the longitudinal axis. So with bad yaw gains and either a sharp edged gust or a sharp edge yaw input, it would start this mode in the frame, and the frame would start torsionally flexing, and then it would quickly lose control and crash. So this really is something that you need to take into consideration when you're choosing a control allocation strategy, because it actually may impact some of the structural dynamics. So now what might we do about some of these vibration problems? Well, one of the first things we can look at is a passive vibration attenuation method. So this would be like incorporating spring in place of structural elements in the frame, or by modifying the structural elements in the frame to try to extract some energy and modify the response. So here we've reimagined the state space form just a little bit. And while it looks like it has feedback control, it doesn't. This form is merely for convenience. So we're going to assume that there's no control input here. And the B matrix is structured in a way that the entries, I'm going to call them the activation. So they represent the activation of the element in the direction of motion. So for example, if your element was aligned in the direction of motion, the activation would be a 1. If you had multiple elements, then you would have 2 or 3 or 4. And then if your element was at an angle to the direction of motion, this activation could be less than 1. And why I do this is because now we can use some tools like root locus to place the pole where we want the response of the vehicle to be. And the gain value we're reading is then the required spring and damping constants. And this picture on the left shows a small viscous damper that's used in a radio control car that is of a scale that could find its way onto this particular vehicle. Now, another method is using some sort of active vibration attenuation. Again, because this is an overactuated configuration, we could allocate some control power to being able to modify the response. So this would be similar to higher harmonic control, which is something that's been experimented with in conventional rotorcraft. But instead of, for example, modulating each individual blade to try to tailor the vibration response of the vehicle, here, because of the unique geometry of the individual rotor to try to tailor the response. This time, the state space form really does have feedback control, and the B matrix contains the control derivatives of each individual rotor. And you can see here now when we were discussing, looking at the vibrations, how instrumentation on the frame would certainly help in this aspect. So once again, we could use tools like root locus to be able to determine the appropriate gain values and the response we want. But I have to say that one of the major downsides of an active vibration attenuation method is the actuator bandwidth requirements. As we saw for the first instance of structural damage, the predicted frequency is around 36 hertz. And this is well above the the max speed of the actuator and above the actuator bandwidth. So it's possibly not likely that we're going to be able to modify that particular response by using the individual rotors. However, we did see later on that the actuator feedback may have actually initiated some damage. So with appropriate inputs, we could control some of these modes, because we've kind of seen it in the opposite context where it created damage. But again, with appropriate inputs, we could actually suppress some of this motion. And then another idea that I had that I didn't have a lot of time to flesh out, but it's this idea of semi-active vibration attenuation. So here we do something like include more traditional passive elements, but maybe have an actuator that could slightly change the geometry to be able to affect the response and how these elements behave depending on, for example, the flight condition. And the picture on the right actually shows little brushless motors that are used as wheel brakes for a radio-controlled aircraft. So these are hooked into a little motor controller, and depending on how you modulate that motor controller, you can effectively change how you're extracting energy from these wheels. So by incorporating this into a mechanism on the frame, we could modulate this to kind of tailor the response. And one of the benefits of this is it should relax some of these actuator bandwidth requirements, because it's unlikely that we're going to need to modulate these items at the same rate as a true active vibration attenuation method, because we're likely just modifying them depending on the flight condition or the operations of the vehicle. So this should be able to be done at a lower rate. And all of these methods should be balanced against the performance, the requirements of the vehicle, and then the weight increases from adding these elements, and see, if it's worth putting these on or implementing these.
Colin?
Yes.
Sorry to ask a dumb question, but on your third design, you only had one resonance frequency within the band of terror, so to speak.
Okay.
And you pushed the other ones up. So
Yes.
Could you just on the fourth design, push that last resonance up by some stiffening technique, or why would you not do that?
That's a really good question. And actually, one of the last slides, I talk about this a little bit, but right now, because of the planar nature of the frame, it's pretty difficult to work on this. So we would have to put in maybe a really large diameter tube as the fuselage to try to stiffen the longitudinal axis here in torsion. But if we have something like a 3D frame, then we can put some structural members out of the plane. They could at least affect the out of plane motion of the arms. So if that was the mode that was problematic, we could do so there. Or like I said, we may have to change the geometry of the fuselage altogether. But right now, because of the nature of this particular airframe, we don't have a lot we can do besides using some other sort of method to be able to control this.
I mean, I'm not a mechanical engineer, I'm on the electronic side, but 10 hertz seems to be a pretty low resonance frequency.
Yeah, and that also has to do with the weight distribution. So actually, in my initial design, before I even flew the helicopter, I wanted to put batteries in each individual rotor for some potential span loading. Not that that would have really even helped me here, but after installing the rotors and noticing that it did have some frequencies that were pretty low, I chose to put the batteries as close to the center line as I could to try to at least not exacerbate the problem and make the resonance frequencies lower. So yeah, we might even be able to do some stuff like reducing weight that could affect that resonance frequency and bring it up. But one of the easiest things to do would be redesign the entire fuselage here. Larger diameter carbon tube, for example, would be an easy way to at least increase some of that, at least increase this particular torsional natural frequency. But yeah, it would require a bit of a redesign of the frame.
Okay.
All right, so now let's look at a stability and control allocation analysis for the vehicle. So because of the symmetry of helicopters and this frame, we can extend the longitudinal derivatives that we've developed for the vibration analysis to the lateral and directional axes with some sign changes, and of course, being mindful of the changes in moment of inertia. We also need to introduce some new stability and control derivatives that come from the configuration of the aircraft. Here we see the yaw damping that comes from the rotors moving in the plane. And then we see the yaw control derivatives that either arise from cyclic pitch control or from collective pitch control. We also need to introduce some new derivatives for control derivatives relating to changes in RPM to create moments and forces in that way. Now, we're going to look at this in a more typical flight dynamic standpoint. So these matrices are what you would see, a typical flight dynamics. But the B matrix here, this is from the pilot's perspective, and that'll become important when we talk about the control allocation study. But right now, this doesn't care about the particular control allocation strategy that you use. It just cares about the pilot moves their controls in a certain way, and the vehicle responds in a certain way. But we're going to have to read this a little bit when we get to that control allocation strategy part. So after computing these stability derivatives for each individual rotor, we're going to extend these to the entire vehicle. And then we can make an assessment on the hovering stability of the vehicle as a whole. So we see that it has 4 subsidence modes. We have roll, pitch, heave, and yaw subsidence, and 2 slightly unstable pitch and oscillatory roll modes. Now, calculating the time to double for these slightly unstable modes, we see it's about 7 to 10 seconds. However, this wouldn't really be a problem because we're going to use augmentation anyway, so we can almost place these poles where we want for the appropriate handling qualities. But the reason I was interested in this is because there was one instance where I was flying the vehicle where I forgot to switch it into stabilize mode, basically forgot to turn on the stability augmentation, and I was actually able to take off the vehicle and almost establish a hover. Now, I quickly realized my mistake because of the extreme pilot workload, but up to this point, I wasn't even convinced this could happen. I thought the vehicle would probably just flip over. So I wanted to figure out, what may have made that possible. So certainly the time to double being long enough would make something like this possible. But then this really got me thinking, what makes a helicopter difficult to control? And thinking about it a little bit more, these 4 subsidence modes, they're stable. And that's actually critical for this to be able to happen. But if you notice, they lack a restoring force, right? They're just damping. So what this means is that in hover, the pilot needs to consistently put small inputs on basically all 4 of these controls to be able to maintain hover. So there's a lot of pilot workload compared to other aircraft that have some amount of restoring force. And this is one thing that makes helicopters difficult to control. I also wanted to see how the poles migrated as you change things like RPM and change thrust. Because we're trying to develop a vehicle that could accommodate different payloads and they could operate at different RPMs. And operating at different RPMs is not something that's really typical for helicopters. Generally, you fix the RPM within a narrow range. And this is largely for vibration consideration. And we've seen a lot why that's the case. But if we're trying to operate the vehicle at different RPMs, even though we're going to use stability augmentation, this would be important for maybe understanding a gain schedule. So I was curious and I wanted to see how the stability would change with changes in these parameters of operating the vehicle. So now for the control study, we again start with the individual rotor control derivatives. And once again, we extend these to the entire configuration. So first, we're going to look at it from the pilot's perspective. So right now, this is the current control allocation strategy used. So it uses all cyclic pitch except for altitude control. We do bring collective pitch into the mix. Then we're going to look at pure collective pitch control. And then we're going to look at pure RPM control. Now, some things that you'll notice is that with RPM control and collective pitch control, we cannot generate in-plane forces, specifically in X and Y, like we can with cyclic pitch. So that's one of the interesting things about using cyclic pitch as a method of control. And as a sanity check, just comparing specifically the moment control derivatives, looking at cyclic pitch versus collective pitch, we see the ratio is around 3.5 to 1, something around that number. And so this would suggest tentatively that 3.5 degrees input of a cyclic pitch equates to about 1 degree of collective pitch. So it gives you a little bit of intuition about the size of the response by using each individual method. And like I said, as a sanity check, if this number had exceeded the range, we might think, hey, we've flown the vehicle, it worked, what went wrong? And the same thing, comparing collective pitch and RPM control, the ratio is about 20 to 1 for those moment derivatives. So this would suggest that a change of 20 radians per second equates to about a change of 1 degree of collective pitch. That's about 190 RPM. And again, this seems pretty reasonable. 190 RPM is about 10% of the available control, and 1 degree is about 1/12 of the available collective pitch control. So as a sanity check, because these are just predictions, this seems reasonable to get us started. All right, so now looking at the control allocation study, as I mentioned, the B matrix on the right represents the aircraft from the pilot's perspective. So again, doesn't care about the control allocation strategy, just that the pilot moves the controls a certain amount, the vehicle responds in a certain amount. So this would also include things like the transfer function from how far the pilot moves the controls to how much the swash plate moves or the blades change angle. However, when we're looking at the control allocation study, we're going to look at the B matrix from the rotor's perspective. So now we're behind the pilot's controls. We don't care really what they're doing here. We care just the methods of control available at the rotor. So now we have collective pitch, cyclic pitch, and RPM control as a method. We combine these into a larger B matrix, and then we develop 7 different control allocation strategies. We have cyclic pitch only. So now we don't even have a method to control altitude of the vehicle. Then we have collective pitch only. We have RPM control only. And then we have some combinations. We have cyclic pitch and RPM. We have collective pitch and RPM control. We have collective and cyclic pitch. Now this would look like the current control allocation strategy used, but now collective pitch can generate moments in the vehicle. So this is slightly different. And then we have all the available methods to us. So to be able to compare these and make an analysis between them, we follow a method from Humbert and Farouk, where we start with SciC, which represents the time history of a control input. And then from this, we can recover the controllability Gramian by solving the Lyapunov equation. What's special about this is the eigenvectors and eigenvalues of this controllability Gramian represent the principal axes and lengths of this shape. This kind of like an ellipsoid or hyperellipsoid. And by moving along one of these axes, by following that direction, that essentially tells us how far we can go with the states by a unit input of control energy. So by maximizing the length of these axes, by maximizing the volume of this shape, it can lead us to minimizing the power and minimizing the number of actuators. So minimizing the control power and minimizing the number of actuators in the vehicle, which is certainly something of interest. Another thing we must do here is we must normalize the control inputs. So to do that, we start with the maximum input and then we subtract out the trim value. So now it tells you that it also depends how the vehicle is operated. For collective pitch, we have 18 degrees maximum, and then we subtract out the trim value at hover because the blades will have some sort of positive angle. For cyclic pitch, we don't have a trim value here. Maybe if we were analyzing with a wind, we would have a trim value of cyclic pitch, but right now in hover, it's all good conditions, we don't have any trim value. For RPM, of course, we have a trim value, and the maximum value is from the prediction of the gearing, the battery voltage, and then the motor constants. And this leaves us with about 12.6 degrees for maximum control input for collective pitch, 7.5 degrees for cyclic pitch, and 1860 RPM for RPM control. Now to compare these, we either compute the determinant or the first Frobenius norm. And largely these two results look the same. They're just a little bit different way to look at it. But one of the things you'll notice for the determinant is that the cyclic pitch drops away. This is because we do have that uncontrollable state in the vertical axis where we cannot control altitude. It does show up a little bit with the first Frobenius norm, but it's really small compared to the other control allocation methods. So now looking first at RPM as a control, we see that we do have a flyable vehicle. And then if we add cyclic pitch as a method of control in addition to just pure RPM, we do have a slight increase in the size of the reachable sets, but it's not that significant. Moving to collective pitch, we see a big jump, and then we see the same thing where adding cyclic pitch as a control only increases the reachable set just a little bit. Now, of course, with all three available methods, we have the largest reachable set. But you might ask yourself here, well, collective pitch gets us most of the way there, and then adding RPM, really, there's not much of a difference adding cyclic at that point. Might we add something like cyclic pitch as a control? Well, this could largely depend on the requirements of the vehicle and the requirements for flight. So for example, I've made a claim that this vehicle could potentially perform auto rotations, and that's actually something that really captured my interest at the beginning of the project. Well, using collective pitch is critical during an auto rotation. So that is one control that we must have if we want to be able to fly in that flight regime. And of course, during an auto rotation, we're not going to be able to control the RPM with the motors because we're going to assume that the motors don't work in that case. Now, there's some reason to believe that just using collective pitch as a control, while this would normally work while the vehicle's under power, in auto rotation, we can have a severe degradation of the yaw authority by using collective pitch as a control. So you can see here, by bringing in cyclic pitch as a control, we should be able to recover some of that yaw authority and then safely pilot the vehicle. So while it doesn't increase the reachable sets a lot, it might allow us to have a wider flight envelope and explore some new flight regimes. And I want to say also about these results, these don't include things like control latency. And so that's one of the major benefits of using blade pitch as a control. By using the servo actuators and the blade pitch, you have a large reduction in control latency when compared with using RPM as a control. And so that wasn't incorporated into these results, but that's something to keep in mind. So we see these benefits with collective pitch and using cyclic pitch, even without incorporating that, which is another benefit for using certain control allocation strategies. And what's also interesting is when you look at the size of the reachable set as a function of RPM, we see that a number of these methods enjoy a larger reachable set as the RPM is increased. So this is not only because the control derivatives, specifically the ones regarding collective pitch, increase in value as we increase the RPM, but also we reduce the trim value of the collective pitch angle at hover as we increase the RPM. So this gives us a little bit more that we can use for control. And so you can see here that we're operating the vehicle at about 1700 RPM. But what's interesting is above about 2200 RPM, these methods kind of collapse together, right? So the ones that involve RPM, you can see those degrade because we're increasing the RPM. We have a less available to us for control. But all these other methods get better. And at some point, they basically are the same. So what's interesting is if you chose to operate the vehicle at this higher RPM, if you're only after the largest reachable set, then really collective pitch is the only control you need. Bringing in cyclic or RPM doesn't really help you out here. It's only this narrow range where maybe between 1200 RPM to almost 2000 that you do get a little bit of a benefit, specifically by using RPM in this case. And then another interesting thing here is that really we see that RPM doesn't help us all that much, again, depending on where you're operating. So this almost validates the choice that we made to not use RPM as a control, just fix the RPM and use blade pitch as a control. But again, it depends on how you're operating the vehicle.
Why is that?
Why do they collapse onto each other?
Yeah.
Well, so we can see that.
Is there like an intuitive explanation, or is because you have gone through all the mathematical analysis, assuming everything's correct, and you came up with a startling conclusion? Is there some intuitive explanation?
Okay, so I think here's the easiest explanation for RPM control specifically and why it really doesn't add much value. As we increase the RPM, because we have a maximum voltage from the battery and then the motor constants are essentially fixed in the gearing, as we get closer to that maximum RPM, we have less available overhead for control. And so when I was doing a lot of experiments with fixed pitch multi-rotors, I did find kind of anecdotally that above about 70% of the throttle position, the vehicle would often become unstable because there really wasn't enough available left to control the vehicle. So, I mean, typically you kind of shoot for maybe operating the vehicle at about 50% RPM. So that's where hover would be. And here we can see that, we do still have RPM as a method of control. Maybe we even get a little bit benefit by adding it to collective pitch. But as we go much higher, we just reduce the amount that we could use for control. And at some point, we lose control of the vehicle. So at least for RPM, I think that's kind of the intuitive way to explain that. Why cyclic pitch doesn't have as much of a value, that's something that I kind of expected. Maybe it did a little bit more, but I think it shows how powerful collective pitch is as a method, especially because you're generating a force at a distance versus trying to generate some moments by tilting the lift vector of the rotors. And that also depends on how rigid the rotor is and the rotor mechanics. And so if this is, and also how high the rotor is above the CG. So that might change depending on some different geometric parameters of the vehicle. But I think really it's testament to using collective pitch and specifically, how effective it is to generate moments by that force at the distance from the frame. Does that help?
This is Bob on the intuition part. I think you can fly faster with cyclic pitch.
Yeah.
And that's a big deal.
Yeah, what's interesting is also I was reading another one of Ray Prouty's articles, and it also suggested that say you have a tandem rotor configuration. So just eliminate two of the rotors in this particular vehicle. If you just had collective pitch for control, to trim the vehicle in forward flight, you would have really large body angles. Now, if you had sensitive payloads or you had passengers on board that really didn't want to be inclined that much, by introducing cyclic pitch, it helps you trim the vehicle at better body angles, and that would certainly reduce drag and increase speed. So yeah, absolutely bringing cyclic pitch in. As I mentioned, while the analysis doesn't necessarily show that it's beneficial, I think by looking holistically at the vehicle and how you want to operate it, can really bring collective pitch back into the mix and show that it does have value. Like I said, I was at an interview not too long ago, and I was describing the project, and they asked kind of a weird question. They said, what's a win for the project? And I really didn't know how to answer that because I really just kind of want to get to the bottom of this. But what I explained to them is that I couldn't answer that question effectively unless I knew the requirements. Certain requirements would make it a win, would make collective pitch and this particular configuration and the control allocation strategy very successful. But if we just want to go fly a camera outside and take some pictures, I would still argue that I think a fixed pitch multi-rotor is probably better in that regard. It's more mechanically simple. It's pretty proven. So I have to know more about what's going on before I could make a complete assessment of certain design choices.
Well, I think when you scale this thing up, which is inevitable, you'll find it. My guess is, I'm a fixed wing guy, but that the advantage of cyclic will be greater. Scaling this thing up, the inertias get a lot easier because the inertia goes with the fifth power of the scale factor. So things get nicer as you go faster. Also.
Very interesting.
And I'd like to comment here on the advantage of this configuration versus just a conventional one, even for the simple example that you mentioned when having a camera and just flying it in a nice day. The conventional configuration suffers significantly when we lose one rotor, right? It's not robust. Basically, it will keep revolving around, yawing around itself until you hopefully land it safely, right? But this one, if we lose a rotor, I believe it's still functioning.
Yeah, so if we had a quadrotor configuration and our requirements specified that we must have a quadrotor configuration, absolutely. In a normal fixed pitch rotor vehicle, we lose one rotor, the vehicle becomes uncontrollable. If you don't power down the rotor across the diagonal on the frame, the vehicle tumbles. And unfortunately, I've encountered this before. If you shut down that rotor, then you have no balance of the moments in the yaw axis and the vehicle starts spinning. So what you could do here is if you lost one rotor, instead of powering down the rotor on the other diagonal, you could set that to flat pitch. So it's not producing any thrust, except maybe a little bit necessary to balance any forces on that diagonal. But by keeping that rotor running, what you could do is you can adjust the cyclic pitch as an input to be able to help nullify the yaw moment generated by the other two rotors. And then essentially now you have like a tandem configuration just with an extra rotor hanging out there helping you when you need it, and you should be able to make a safe landing. So yeah, it has a lot of robustness, especially if you have, we'll call it precious cargo, which certainly people on board of these aircraft is precious cargo as it gets.
Mm-hmm.
Any other questions on this?
Yes.
Yes.
How I didn't quite understand the previous discussion about how it scales. So just out of curiosity, let's say you scale it up to human size. What happens to all these resonant frequencies, and does your analysis still hold, and how would it have to be modified?
Well, in terms of the specific analysis holding, I couldn't guarantee that. I don't see any reason why at least this reduced order model wouldn't have some applicability as we scale this up, because we can do some similar things with the structural dynamics and calculate the stability derivatives. I think you introduced some new interesting thing about the flexibility of the blades, for example. At this scale, we do benefit from things just being a little bit stiffer. For the airplanes that we build, we often have trouble. We would have trouble making them, not strong enough, because just how we've scaled down the materials, we kind of enjoy with just some simple designs, pretty strong and often stiff structures. So as we scaled this up, yeah, I couldn't guarantee that it worked, but certainly some of these ideas about the aerodynamics, from the aerodynamic standpoint, bringing cyclic pitch in would have benefits, and bringing, blade pitch in as a control, because, if we have large rotors and we're trying to vary the RPM, there's a lot of inertia in those rotors, especially as we start increasing the size and they need to carry heavier loads. And so this could affect at least the control power or even the stability of the vehicle. And using blade pitch as a control is pretty borne out in a lot of helicopters. So yeah, there are vibration issues, and certainly bringing in more energy will have problems. As we saw in that first video, when they scaled it up, there were significant issues. So it's something that has to be addressed, right? And I hope this is kind of a step along that way by starting with small vehicles and scaling it up a little bit and doing test flying and then moving up. I think it has to be kind of systematic for safety.
Yeah, I guess it's kind of a fair question and an unfair question, because you've already done a lot. So, it would be a whole new project to do it at full scale. But you showed at the very beginning pictures of the full scale models having structural failure. And you've thought a lot about all the resonant frequencies and the mechanical stabilities. I'm just curious, gut check, I'm not going to hold you to it. It seems like your 10 Hertz resonance frequency that actually carries through to full scale, and it would still be in the tens of Hertz frequency range, and it wouldn't push up to really high frequency or down to really low frequency. So the overall approach would still work. Is that what you're saying?
Yeah, I think I could commit to at least saying that at the beginning. Now, what I'd say is, depending on the structural arrangement, you can kind of tune the vehicle to how you want it to respond. So yeah, if we threw on a lot of material, we could make it quite stiff. Obviously, we have to balance that against the performance. But one of the things that's critical is at those larger scales, we're operating the rotors at a much lower RPM. So we do have to be mindful of that. As we scale up, we're going to scale down the RPM of the vehicle. And so now we bring in that band of energy, and even the multiples of it. If we have 3 blades, 3 times the RPM, 5 blades, 5 times the RPM, that actually starts to maybe get into this range that this vehicle's at. So as we scale up too, we have to look at how the rotors are operating.
Okay.
I'm not sure I understood you correctly, Colin, but when you scale up, you don't want to throw more material at it. When you scale up, you increase your geometric dimensions, which drives your moments of inertia very large with small mass, and actually reduces your stresses. So I think you find that things get better as you get larger.
Yeah, Mike, I'll use the analogy. When we did the BWB, we're flight testing a 8% model up at Dryden. And we looked at the inertias to match the full-scale inertias, or the full-scale airplane, with an 8% scale model. We almost had to build the outer wings out of Kleenex. And so we settled for matching the relations between the products and moments of inertia.
Interesting.
So dynamic scaling, which applies to this, is having the 6 DOF vectors have all the same angles between them. And you can kind of get to that, but I think this problem is much harder to solve at this size, I won't say scale, than it will be full scale.
Right.
Interesting. Any other questions on this particular one? Okay. So now let's just look at a little bit of potential future work, which is kind of where we were driving at here. Right now we have this planar configuration of the frame, but the frame redesign is one of the major things we could do to try to tailor the response and make it less susceptible to some of these problems. Constraining myself to this planar frame did create some challenges. So being able to put elements that come out of the plane can help us with stabilizing these out of plane modes, and being able to tailor the geometry and size of the fuselage can help us reduce some of those torsional problems by increasing the stiffness on those particular axes. As I mentioned a little bit before, it would also be important if we're after trying to understand the vibrations better and then use some sort of active vibration attenuation method to provide instrumentation on the frame, maybe placing a bunch of accelerometers at different positions to try to get a map of how the vehicle is vibrating. And then if we're using an active vibration attenuation method, these would be fed into a microcontroller. There'd be some predictions about if the vehicle is responding in this way, let's put in this input. And those accelerometers can help us achieve that. So the frame design and instrumentation would be kind of a critical first step, because really what I was after initially is I wanted to fly the vehicle and start exploring this wide flight envelope. But since I had these problems where it was creating damage, I now took a detour and was trying to make the frame more robust so I could then go back and start exploring this flight envelope. So by making a robust frame, you can at least eliminate some of those concerns while you're trying to explore other aspects of the vehicle. And I think that's an important first step. Another thing is some sort of control allocation validation. Right now, all these stability derivatives and these control allocation strategies, they're predictions. And by doing some more bench testing of the rotors, by doing some more flights with the vehicle to try to substantiate these claims and validate at least the predictions for the stability and control derivatives, will be important to make an assessment of how you want to set up the control allocation strategy and maybe how you want to pilot the vehicle. And then it'll be important to expand this analysis and flight testing to other flight conditions. Most of the flight testing took place around the hovering condition, and all of the analysis took place around the hovering condition. But extending this to forward flight may bring about some new challenges, may bring about some new vibration issues, and may change a little bit how we look at the control allocation strategies. And this is even not including having other elements on the frame, like if we have little lifting bodies, or even including aspects of the frame that generate moments and drag. And then I think a long-term goal, and we were kind of talking about this a little bit earlier, is to try to extend this to other configurations, make it a little bit more general to, I guess, different sizes, different number of rotors, and overall different configurations, because at the beginning we saw that most of those vehicles look more like airplanes with rotors on them. And so, you have this blending together of aircraft design and rotorcraft design, and there's certainly going to be structural interactions. And people that have a tendency to make the wings really long and slender might find out if you put large rotors on it, large masses at the end, this could create some unique problems. So being able to extend this analysis to larger vehicles, different amounts of rotors and different configurations will be really important, I think, moving forward. And again, to make an assessment of this method of control and other design choices made. Any questions on this stuff?
Colin, it's not a question, but when you bring up allocators, I spent a lot of money at Boeing doing the control allocation for BWB. I wasn't doing it. Two very good people were doing it. But BWB, the whole trailing edge is control surfaces, and you can get pitch, roll, or yaw out of a lot of them. And which ones do you use and still leave control power in all axes and so on? You have laid the foundation here, I believe, for a lot of work, good work on scaling this thing up and then looking. Control allocation will yield big benefits when you finally get it right. And this is a preface to full-scale ones that will be amazing.
Oh, thank you. I appreciate that. And yeah, absolutely. On a lot of these eVTOLs, you have rotors at different sizes and different locations on the vehicle. So certainly we're just starting with a square here, but that analysis being more general is important for kind of the future of that study. So I really appreciate those comments. Thank you. Before we finish, I wanted to share a little anecdote. So I was thinking not too long ago about what the genesis of this project was. And I actually realized that it seems to stem from what I'll call kind of a failed job interview that I had at a local company. I had gone in and I brought a 3D printed quadcopter to try to showcase some 3D printing skills. And I had a passion for rotorcraft at the time, but I didn't know a lot about being able to predict the performance, even some of the design choices made on that. And the interviewers were asking me a lot of questions. You know, how'd you make this design choice? And what would you do to extend the endurance of the vehicle? And I really didn't have good answers. So needless to say, I didn't get the job and I left a little bit frustrated, but I went home and I said, you know what? I have such a passion for rotorcraft. Not only do I not want to be stuck in that position again, but I want to know more about these. I want to be able to talk more about it. So I started reading some books I had about it and test flying that quad rotor. And I quickly became very fascinated with trying to predict the performance and extend the endurance of quad rotors. And it got me thinking, well, hey, as these scaled up, would I have problems with fixed pitch rotors and varying RPM? I'm really familiar with model helicopters. Could I integrate those rotors into this type of configuration? So fast forward a little bit, and hate to say this, but I was actually feeling a little disillusioned and thinking I might drop out of the PhD program. And I had this idea in my head for a while, and I said, you know what, this might be my last chance to build this. So I poured in some money, had some time, and built this. And the key thing is that it worked, and then it had the failures. Had it just failed spectacularly, not worked at all, I probably would have been frustrated, put it aside. Had it just worked and only worked, I probably would have said, that's cool, put it aside. But the fact that it worked and then had these problems and then made changes and repairs and it had more problems made for a very interesting problem that I wanted to dig into and understand better. And so as cliche as it sounds, I've really benefited a lot from measured amounts of failure. And I was thinking there was a time where a friend and I, we got a little bit bored with building conventional airplanes because they became a little formulaic and we kind of saturated on our learning. So what we started doing is we started building a lot of unconventional configurations and making unconventional design choices, because when these failed or, you know, they had problems, and then we're out in the park cutting stuff off the airplanes, adding stuff on the airplanes, and seeing how all the choices were interconnected, we really gained a lot of learning. So again, when those were failing, that's where we really gained a lot of knowledge. And when I've helped people, I've tried to encourage them to dive in and try something, because I think there's this tendency to want it to be right and perfect at the beginning. But when it doesn't work, as long as you're learning from that, you can really get a lot out of it. So yeah, as cliche as it sounds, I've benefited a lot from measured amounts of failure. And I have to keep reminding myself of that, because of course, you know, I don't want to fail, but it has led to a bit of success. And before we conclude, I wanted to just say I'm extremely grateful to everybody who has helped me for so long. I want to, of course, thank my family and friends for their continued encouragement and support through so many years and so much stressful time. I want to thank all the professors and mentors that I've had for so many years here who have provided a lot of guidance. Of course, a special thank you to Professor Taha for being a very kind and patient advisor. He really let me navigate this kind of on my own terms, which had to have been frustrating and certainly not the most efficient, but I think it's kind of what I needed to be able to make it through. And Professor Liebeck has been an extreme advocate for me and a very kind and encouraging mentor. So I want to thank you so much for that. And Professor Peter Burke, thank you so much for being part of the qualifying committee and being part of the dissertation committee and sharing your passion for autonomous aircraft. And you know, I have so many people I want to thank. It could be a presentation in itself, but I want to just end by saying this could not have been done alone. This is really a team effort, and I've benefited so much from working alongside people and being inspired by them and seeing their passion, and friends and family and mentors encouraging me. I could not have done this without that. So I'm really, really deeply indebted and have so much gratitude for that. And I just want to thank you so much.
Thank you, Colin. So, I don't know, there are some reactions here for clapping.
Thank you.
Thank you, man. Yeah. Well done. Let's see if anyone has a question. Anyone from the audience has a question, and then we will move to maybe breakout room. Anyone has a question, please? Professor McCarthy, please. Go ahead.
Colin,
Yes.
I want to thank you first very much. This is a very interesting talk, a very interesting design for a innovative rotorcraft, and I'm so pleased to see where you have come in terms of your research. I just have a couple simple questions just to help me understand.
Okay.
Your very first design was a design that you felt was comfortable to fly. As
Yes.
you change the designs, you increase the stiffness, move the natural frequencies, yet seemed to suggest it became less comfortable to fly. They required more effort.
Yes.
Is there a balance between those? Could it be that living with low natural frequencies, but being comfortable with flight is something that you could achieve?
Yeah, I think that's absolutely very possible. And that's kind of what inspired those ideas about vibration attenuation, because yeah, absolutely. As these the structural elements were changed, the structural arrangement was changed. What I've seemed to notice is the vibrations that are making it to the flight controller are more significant. So this is making it harder to tune the flight controller, and that's making it more difficult to pilot. In addition to me being very nervous, and that's on me, right, at piloting the vehicle, but being nervous about it causing incurring damage. So one of the things that I didn't have initially that I've outfitted the frame now is the GPS system that hooks up with the flight controller, so I can try to take me out of the equation as much as possible, and then be able to make more sound choices by eliminating that variable. But yeah, I think that, as you mentioned, there could be some balance. Now that we know a little bit more about what can excite the frame and what seems to be susceptible, we can then try to at least stay out of that range and possibly have a vehicle that can fly at least within a narrow window of the flight envelope and maybe narrow range of operating RPMs with success, because we did see that the first time. And one thing I have to mention, I couldn't really find a good place in the presentation because the presentation was long as it is, but there was a little bit that happened in between frame design 1, frame design 2, and subsequent. And between frame design 1 and 2, there was a slight incident where there was a minor crash of the vehicle, and I needed to make some repairs. So there is a possibility that some of the carbon tubes may have incurred a little bit of damage, although they broke pretty consistently with how the FEA model predicted. But one of the things I noticed that made a huge difference, I doubt I can even show the picture that really makes it make sense, but these are 3-bladed rotors. For most of my model helicopters, it uses 2 blades. And when you buy helicopter rotors, generally they come in sets of 2 that are balanced and matched to each other. Well, for 3-bladed rotors, not only is it hard to track the blades, but buying new blades when you have a crash is kind of a pain because there's a large number of blades and usually you break quite a few. So what I did is I found a different blade. Let me see if I can find even a small picture of it. Yeah, you're probably not going to be able to see it, unfortunately, in the picture. But these blades, they're the exact same plan form. They're almost the exact same weight as the current blades that come with the helicopters, but they only come in sets of 2. So I had to buy a ton of blades and try to match them to each other and find balanced sets and put them on the vehicle. And so in frame design 2, it had those new blades. And I was actually kind of convinced that those may have caused some problems. So for frame design 3, I went back to the original blades. It just cost money to do that. But I found it kind of interesting because even though they look identical, have the same weight, almost the same location of CG, if you just do a little cursory test and clamp the blade to the table and flick it, these vibrate at a lower frequency. It's kind of noticeable. And that may have influenced some of the vibration characteristics because how the blades vibrate really does influence the helicopter vibrations. So there were some other changes behind the scenes that also led to some of the difficulty in tuning it, piloting it. And I think that, trying to do a few different steps at once was a disservice to myself. And certainly with more money and time, I could do a little bit better process. But yeah, so to answer your question, sorry, I kind of wandered off there. I think, yeah, there is a good balance of not having too many structural members that are adding weight and having a vehicle that can fly. It just may not have as wide of a flight envelope if you need to stay out of certain regimes.
If I could follow up,
Sure.
just real quick, and then I'll leave you alone. As you add stiffness and increase natural frequency, well, let me just say that it seemed to me what you were showing, and I believe what I heard, is that you were getting energy communicated among your different rotors. And that would be influenced by increasing stiffness. In other words, your first rotor can affect your second and third and fourth rotors better if it is more stiffly connected to those, which is what happened as you increased your stiffness without increasing damping. Because I'm so familiar with your experience with aircraft, I just have to ask this question. Why did you not go to a balsa wood and monocoat structure? Why did you go straight to, or it appears that you went straight to a graphite composite? A balsa construction and monocoat would have given you higher cross sections with higher moments of inertia, and also a little bit more damping.
Yeah, I think that's a very fair question. So I think my initial response is a lot of it was about convenience, with a little intuition about the carbon tubes being a little bit more, I would say a little bit more damage tolerant under normal operations.
That's true.
Easier to prototype and work with. I mean, I love these carbon tubes. It's really hard to see what they are. The company doesn't make them anymore, but there are these beautiful carbon tubes that are pultruded, which normally wouldn't have good torsional rigidity, except they have a 45 fabric sleeve over the top. So in terms of carbon,
No,
it's almost
sounds
as close.
good. No, they're also, it's sizable too.
Yeah.
I didn't quite appreciate the size until you held it up to your body. So, I mean, I'm not saying that that's not a good choice. That's not, I think the sensitivity to damage is definitely true when you're building something that physically large.
Yeah, and so I never really considered balsa. That's an interesting thought. What I did consider though is after the first instance of damage, and knowing that when carbon tubes break, they break, right? You don't get much warning and they just fail. So I thought, okay, well, maybe I should.
They're also particularly vulnerable to vibration because yeah.
Yeah, and so I was thinking when I was doing some redesigns, well, should I incorporate some aluminum tubes, for example, into the structural members, which may not damage as violently, but when I was coming to the conclusion doing some of the analysis, I thought, well, it seems that right now I'm dealing with problems with low natural frequencies. I want to do everything I can to increase those. And I didn't want to compromise on, the modulus of elasticity. So I did consider slightly, but I think part of circling back in that future work of frame redesign would be considering other materials. Absolutely.
Thank you.
Thank you.
Questions? Thank you, Professor McCarthy. Professor Dimas, Professor Johnson, Professor Thomas. Any questions if you have, or Colin's friends? As I always say, this is your last chance to revenge.
Oh, geez. Go easy on me.
Any questions, folks? Everything is crystal clear. I mean, we can have the committee also, Professor Liebeck and Professor Burke. We can have regular questions here, and maybe we can break out with Colin alone to embarrass him more.
Oh, geez.
One point I'll make on the difficulty with these things is the aerodynamic interference of the framework. And so going to a larger section, you've got the downwash from the rotors getting interfered with more.
Yeah.
Oh, interesting.
Yes.
Yeah, there's another slide that I couldn't include in the normal set, but some of the first experiments I did were trying to understand the interaction between the rotors and the airframe, because somebody had come to me with a quadrotor that didn't fly, and they were convinced that it was the electronics. And I took one look at the frame and I said, you know what? I think there's too much area underneath the rotors and that's causing problems. So what I did is I took my quadcopter and I made little plates that I glued underneath the rotors at different sizes and tried to catalog the increase in power as a function of percent disk area that was underneath the rotors. And just a little, just a simple drag analysis actually matched the flight test data pretty well. And beyond a certain amount of area underneath the rotors is a percentage of disk area. And I want to say like 60%, it almost doesn't fly anymore. You can barely lift off the ground. You pretty much have to stay in ground effects. So absolutely, the rotor interference with the frame not only affects the performance, but could affect the vibration characteristics as well. And another thing, again, because it's a planar frame, if we're in forward flight, having the rotors basically in the same level is not generally what's done on tandem rotors, because you do have a bit of interference between the main rotors and the front rotor and the rear rotor. So we'd likely see a frame with different levels where the rear rotors would likely sit above the front rotors. And so there is, even besides the interaction of the rotors and the airframe, we have the interactions of the rotors and the rotors. And that's one thing I was worried about. And really why I want to go try to experiment with auto rotations, I think it's kind of a fascinating problem, is if we're in auto rotation, how does it behave? Are there some nasty interactions with the rotors? I really was having trouble finding anything about auto rotations with tandem helicopters, which I was hoping to find to try to kind of extend to this. So part of the future work would be, some flight testing or CFD analysis, even to try to just get a little deeper understanding of how that might behave, because that's kind of an unconventional flight condition, especially for these things.
Any other questions?
Well, a fix on the downwash on the tubes, they're cylinders. And I wonder if there's Carmen streeting off those, the wake off of those. And a cure for that, though, is just put about an 1/8 diameter vertical fence down that'll knock off the carbon streeting.
Very interesting.
Well, don't go there, Todd.
I had one time.
Right, folks, Colin Alexander Sledge is granted the Doctor of Philosophy in the Mechanical and Aerospace Engineering discipline from the University of California, Irvine. So let's celebrate. Congratulations, Colin.
Congratulations, Colin. We can't hear you.
Super happy. Oh, yeah,
There you go.
the committee is
You
super happy.
can hear me now, right? I have too many computers. Thank you.
Go ahead, man. Go ahead.
I was saying that, Professor Jackie, I'm sorry, I'm going to keep saying Professor Thomas, but Professor Jackie Hearn, she was there the first summer that I was working on this, and I'd come in and tell her how frustrated and this wasn't working. And, I was always nice as a sounding board through all the projects. So thank you. And thanks for being there from the beginning of this project.
Oh, I keep saying Professor Thomas. Oh, congratulations. I'm sorry, I did not notice that.
Oh yeah, no problem. I was married earlier this summer, and Colin was there, so that was fun.
Wow.
Yeah.
Congratulations, Jackie.
Yeah, thank you. But yeah, I just think that for Colin, having a thesis for which you're able to go through the experimental challenges where you had to physically build the vehicle in order to learn what you were able to learn, and to be so thorough about it. I don't know many people who have done that for their theses, and to be able to actually learn and come up with conclusions from it. I think it's very fascinating. I think you're one of the few people who could have done that. So congratulations for that.
Thank you
This
so much for those kind
echoes
words.
the comments from the committee, actually. Thank you, Jack.
Thank you.
All right, guys, celebrate with your friend. Congratulations, Colin.
Thank you.
It was a hell of a ride.
All right. Thank you so much, everybody.
Thank you, folks. Thank you so much. Okay, I'll see you all. Bye-bye.
All right, bye. Thank you
Bye,
for staying
Bob.
up so late
Bye.
to be here.
No, of course.